Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I'm recording this intro from San Jose, California, where I'm attending the NVIDIA GTC conference. NVIDIA CEO Jensen Huang made a bunch of interesting announcements at his keynote this morning, which I live tweeted from my Twitter account @SamCharrington. I'll also be writing about my thoughts from GTC for an upcoming edition of my newsletter, which I'd encourage you to subscribe to by visiting twimlai.com/newsletter. In this episode, I'm joined by Lyne Tchapmi, PhD student in the Stanford Computational Vision and Geometry Lab, to discuss her paper SEGCloud, Semantic Segmentation of 3D Point Clouds. SEGCloud is an end-to-end framework that performs 3D point-level segmentation, combining the advantages of neural networks, trilinear interpolation, and fully connected conditional random fields. In our conversation, Lyne and I cover the ins and outs of semantic segmentation, starting from the sensor data that we're trying to segment to 2D and 3D representations of that data, and how we go about automatically identifying classes. Along the way, we dig into some of the details, including how she obtained a more fine-grained labeling of points, and the transition from point clouds to voxels. Before we jump into the show, a few quick questions for you. Are you an IT technology or business leader who needs to get smart on the broad spectrum of machine learning and AI opportunities in the enterprise? Or perhaps someone in your organization could benefit from a level up in this area? Or maybe you would benefit from them leveling up. If this sounds like you or someone you know, you'll probably be interested in my upcoming AI Summit event. Think of the event as a 2-day, no-fluff technical MBA in machine learning and AI. You'll leave with a clear understanding of how machine learning and deep learning work with no math required, how to identify machine learning and deep learning opportunities within your organization, how to understand and take advantage of technologies like computer vision and natural language processing, how to manage and label data to take advantage of ML and AI, and how to build an AI-first culture and operationalize AI in your business. You'll have an informed perspective on what's going on across the ML and AI landscape, and you'll be able to engage confidently in discussions about machine learning and AI with your colleagues, customers, and partners. I am super excited about this event and the speakers you'll get a chance to learn from. For more information, visit twimlai.com/AI Summit, and feel free to contact me with your questions. And now, on to the show. All right, everyone, I am here at NIPS, and I am with Lyne Tchapmi, who is a PhD student at Stanford in the Vision and Learning Lab. Lyne, welcome to the podcast.
Thank you.
How did you get involved in machine learning and artificial intelligence?
I've been passionate about science and mathematics from a very young age. And when I got to college, I started studying electrical engineering and computer science.
Okay.
I got involved with...
and where was that?
That was at MIT.
Okay.
Yeah. So
I've heard of that.
I participated in the Super Europe program there, which is an undergraduate research program. And as part of that program, I got to work on designing, building, and programming a wireless health monitor that essentially keeps track of cardiovascular signals. It connects to the ear and collects that data and sends it to a smartphone.
Okay. And what was that program called?
Super Europe.
Super Europe?
Yes.
Okay.
So Super Undergraduate Research Opportunity Program. That's what it stands for. Yes. So it was a pretty exciting project, and I found out that I was really interested in both the hardware and the software side.
Okay.
As a result, I continued my study. Mostly on the hardware side, I took a bunch of circuit design courses and continued doing more research. Eventually, I continued with my master's still at MIT doing power electronics.
Okay.
So my master's thesis was on designing an efficient power converter for low power circuits that are used in mobile devices such as tablets and smartphones. So when I finished my master's, I liked research, so I decided that I would apply for a PhD. I got into Stanford. And when I came in, initially, I thought that I was going to continue and work in power electronics.
Okay.
But Stanford has a PhD rotation program. So during your first year, you can spend all 3 quarters working in 3 different labs.
Oh, really?
Yes, so with 3 different professors. And it kind of gives students the opportunity to explore a little bit all of the different professors, all of the different projects that are available. So I took advantage of the program. I worked with Professor Juan Rivas from the Power Electronics Lab. Then I worked with Professor Sebastian Tran, who used to do robotics and at the time actually was more focused on computer vision things. And that's when I learned a little bit about computer vision, thought I was interesting, started taking classes. And during my 3rd rotation, I worked with Professor Silvio Savarese, who is currently my advisor.
Okay.
But yeah, in his lab, that's when I learned about deep learning. I started exploring it a bit more, thought it was interesting. And I think the most fascinating aspect of it was that just the possibility of using the techniques and the tools that are available to solve various problems ranging from energy, finance, construction, medical. So yeah, I thought that was pretty exciting.
Awesome. Awesome. Tell me a little bit about the current focus of your research. What are you working on? In fact, you've got a paper that you're presenting here at NIPS, right?
Yes. So I focus on 3D scene understanding.
Okay.
So my goal is to take visual information about the 3D world and try to make sense of it. And the reason why such information is important is that if you have in intelligent systems that are surrounding human beings and that are able, or in order for them to be able to assist human beings, they need to be able to understand what is going on around us. And some of the applications of that are self-driving cars and just general assistance within the home. Let's say an elderly person who needs help with daily tasks, or even a surgeon in the hospital that needs assistance maybe for getting tools around and things like that. So I have been working, my recent paper is about semantic segmentation of 3D point clouds.
Okay.
So with sensors such as Kinect sensors, LiDAR sensors, you can acquire models of 3D environments. It could be indoor spaces or outdoor spaces. And that information is not meaningful in and of itself. And using deep learning, we can make sense of it. And the goal of the project was essentially to identify all of the different elements that compose the data, the 3D data. In indoor spaces, you might be interested in identifying the walls, the ceilings, the objects, the tables, chairs, and all that. And in outdoor spaces, you might be interested in identifying roads, the cars, and buildings, for instance. So the method that we develop is...
Well, just before you go into the method, just to make sure I understand, I'm imagining we've got a Kinect sensor in here, and it's giving us kind of this 3D point cloud of everything in this room, but it's just points. And so, the points aren't distinguished from, the table, the chairs, et cetera, the people. And so you're applying deep learning on top of that raw data set to then categorize, or is it a categorization problem for each of the points into, some object? And you don't know the objects that are in the field before you do this, right?
Yes, we don't know the objects that are in the field, but we have a certain set of objects that we're interested in. So the thing with deep learning, or at least supervised learning, is that you need to know the classes that you are interested in ahead of time. So in order to first perform the annotation, because the ground truth is needed. So during the annotation process, you essentially choose the classes that you are interested in.
Okay.
And that's what you use for training. So although you don't know all the classes that are available in your data set, there will be a specific set of classes that are used during training and during testing. And usually there's a default class that is called clutter or other,
Okay.
which is used to identify anything else that wasn't labeled in the data set.
Okay.
Yeah.
And so when you're identifying the classes that you expect, is this a small number of, I'm expecting to see, this is a home environment,
Yes.
There's probably, one of these 10 things, or is it like, 1,000 classes, all of ImageNet or something like that?
So at the level of 3D data, it's still a very small number of classes.
Okay.
In part because 3D data is much more difficult to annotate. And so the number of classes range somewhere between 8 to tens or 20 classes.
Okay.
So it's not yet in the hundreds.
Okay.
It's a lot more difficult to annotate 3D data. And the fact that sensors, depending on what modality you annotated in as well, the sensor data could also be very noisy. So it could be difficult to identify certain classes. So, and that's one of the challenges with 3D data compared to images. Images are much easier to acquire. And pretty much everyone today has a cell phone, a camera. So there's a lot of images that are being created
Right.
at every second. And the same, it doesn't apply to 3D data. Not everyone has a Kinect sensor or a LiDAR that they use on a daily basis, essentially. So 3D data is much less available, and then you need those specialized tools to really annotate them. So
Okay.
it's a bit more difficult.
And when you say annotate, are you talking about using your model to annotate, or are you talking about the pre-training task of having, creating the training set by annotating, sample data?
Yeah, so I'm talking about the task before training.
Okay.
The task of generating the data set itself and the annotations that
Right.
are going to be used for training.
Right.
So that is the most challenging part around 3D computer vision.
Even for 2D data,
Yes.
right? My sense is that the folks that are doing annotation at scale have all kind of come up with their own systems for doing this. There's not like an off-the-shelf open source annotation toolkit. I think there should be,
Well,
but I haven't really seen anything like that.
there are various ones that are out there.
Are there really?
Yeah, there definitely are. I think the one that I can think of off the top of my head is called Label Me.
Okay.
So it's available to the research community, and a lot of people use it.
Oh, wow. Okay.
Yeah, so they definitely are for images and also for 3D data. More recently, there was an annotation tool called ScanNet that was released to annotate 3D data. So it makes the task a lot more easier. So essentially, the task is to paint over a bunch of segments in 3D.
Okay.
And choose a class for the segments that are painted over. So it makes the task a lot easier.
But even then, it sounds like you've got all kinds of ambiguity because you're painting in 2D over this 3D point cloud. Is that right? Or are you doing like rotations and all that kind of stuff?
Yeah, ScanNet actually allows you to paint in 3D.
Oh, really?
Yes.
Okay.
So that is, it's more suitable for 3D data. The challenge there is that the reconstruction that is used as the basis of the annotation needs to be very high quality, which is not always the case because the 3D sensors are noisy. And what happens is that you're able to annotate the bigger objects that are more visible, but the smaller objects are still a bit more challenging.
Okay.
Yeah.
So you can easily paint the table, but painting a bottle of water on the table is going to be a lot harder because points will be missing or that kind of thing.
Exactly. Whereas on an image, it's much easier to do that.
Right.
Yeah.
Right. Wow, interesting. I didn't realize that, I've had this conversation with a bunch of folks that are working on this, and they all say, no, there's nothing really out there. We had to build it ourselves.
Well, there are some tools depending on the quality. They're mostly research tools.
Okay.
So they may not be very thoroughly developed. If you want to use it for production, maybe it's not what you want to use.
Right.
But there are tools that are used by the research community.
Okay.
Yeah.
But I imagine then that even if you're trying to do 3D annotation, is it? I'm imagining that it's harder to like get a mechanical Turker to do 3D labeling. Because there's probably some kind of special plugin that has to be used if you can even do it over the web. But then B, just the complexity of like the instructions you give and that kind of thing. It sounds very difficult.
It likely is slightly more difficult than images, but it is doable. Again, the tool that I mentioned, ScanNet, that's essentially what they did. They crowdsourced both the data collection process and the annotation process. So they had people, they had Turkers, I'm not sure if it was Turkers, but they had workers actually annotate using their tool. They gave them instructions and the annotations turned out pretty decent.
Okay.
Yeah.
Interesting. Okay, so we've got we've got some training data assembled. Tell us about your process and how you went from that to point segmentation.
Okay. So essentially for each point in the 3D data in the point cloud, we want to assign it a label. And we wanted to leverage convolutional neural networks since they've been shown to work really well for images. But the data representation for 3D point clouds is not directly suitable for convolutional neural networks. So we have
Why is that?
Because think about an image. An image is it's a 2D array, and it has a level of structure that is suitable for convolutional neural networks. So CNNs kind of take advantage of that structure in the image to do the convolutions.
So you've got an array of pixels, and kind of mapping that to a point cloud. At any level of resolution, you could have multiple points in kind of a box. So how would you translate it?
So the point clouds, when they actually are collected, they come in as a 2D array, but it's more, it's not structured. So it's a set of XYZ coordinates with RGB color. And so it's a bit less structured. So there is no, unless you go through the process of voxelization, which is what we did.
Of what?
Of voxelization. So essentially turning that representation into a grid.
Okay.
And the way to do that essentially is to look at the 3D space and divide the 3D space into a grid essentially, and assign turn your XYZ RGB representation into a different representation which has 4 channels. The first channel is occupancy, which is 0 or 1. And if it's a 1, then it means that space is occupied. And 0 is not occupied. And the last 3 channels are not the RGB color.
RGB,
yes, which usually is the average of all the points that are within the unit grid cell, which I call a voxel. Okay. Yeah. So you have to make that transition from point cloud to voxel. And the voxel usually has a predefined size. In our paper, we start out with 5 centimeters. Okay. And there is an added difficulty with 3D data, which is the added dimensionality. So in 2D, you just have 2 dimensions plus the channels. In 3D, you have the added depth dimension. So that kind of scales the problem and makes it a bit more difficult to solve in terms of memory. So 3D data would take more space when you're using CNNs. And for this reason, when we're using traditional convolutional neural networks, we actually have to downsample our input volume further. So we start out with a 5 centimeter voxel and we downsample it through the CNN. So the CNN would downsample the volume to a 20 centimeter voxel. So at the end, what the CNN outputs is a label over a 20 centimeter grid unit, which is relatively coarse. Yes, exactly. Right. So what our paper explored is how can we obtain, still leverage the CNN, how can we obtain a more fine-grained labeling of our point cloud? How can we label the individual points which come from the original sensor? And to do that, we designed a trilinear interpolation layer. A trilinear interpolation layer.
Trilinear, interpolation layer.
So it's we use it to train during training to train the CNN end to end. And basically what it does is the CNN outputs a set of scores for each voxel in space. For each point in space, we look at the 8 closest voxel centers, and we compute the score of the point by weighing the combination of the weights that are coming from the 8 nearest voxels. So you can think of the closest voxel will be contributing more to the final score of the point than the voxels that are a bit further away from the point. And so we use that during training, and the alternative to using...
And now is this the 8 closest occupied voxels or just the 8 closest voxels?
The 8 closest occupied voxels.
Okay.
Yes.
Okay.
And so during training, the alternative to doing that is simply doing a nearest neighbor.
Right.
So taking the closest voxel and assigning that label to the point. And during training, we find out that actually using trilinear interpolation layer performs a lot better than using nearest neighbor.
Okay.
So that was the first module that we added to our CNN. And in the end, we also used a conditional random field to refine the predictions that are given to us by the CNN and the trilinear interpolation layer. And so the conditional random field essentially defines an energy function that enforces consistency between labeling. Intuitively, you can think, well, if you take 2 points in space, if those points are close to each other, then the probability that they have the same label is high. And so the energy function of the CRF enforces that close points are more likely to have similar labels. And so with our energy function, we are able to refine our predictions, and we use a nice implementation of conditional random fields that was published in a 2015 paper called CRF as RNN. So the CRF is implemented as a recurrent neural network.
Okay.
And the advantage of that implementation is that you can actually combine both the CNN, the trilinear interpolation layer, and the CRF and train them end to end.
Okay.
So that gives like a nice module that can be used for semantic segmentation.
Okay.
Yes.
Interesting. And so, what kind of results have you seen with that?
We've seen great results. So we evaluated our framework on the Stanford indoor space data set, and we outperformed the state of the art on that data set, which was PointNet. And currently, we also have we also tested it on the Semantic 3D Net data set, which is the largest outdoor point cloud data set that is available.
Okay. And
at the time of publication, we're also the state of the art, but I think there is a better method now because that's what happens. But yeah, so currently we are, I guess, the second best method performing method on those data sets.
Okay.
Yeah.
And for these data sets, was the improvement like order of magnitude, or was it like huge, or was it incremental improvements relative to the prior state of the art?
So depending on what we saw was that the best improvement that we got was on the largest data set.
Okay.
So we had about I cannot remember the actual numbers, but it was more significant on the larger outdoor point cloud data set. There was also a pretty large gap between on the smaller indoor spaces data set, but the data set is also relatively small, and so the absolute performance is still a little bit low. And I think as we get more data, the numbers should get better. Yeah.
Now this conversation reminds me of another conversation that I've had here at NIPS. Well, it doesn't remind me of it. It is potentially related to another conversation that I've had here at NIPS. And the idea with the research they were doing is that there are, like here, you've had to, a lot of what your research focus was kind of fitting or transforming this point cloud to the voxels and potentially losing the relationship between some of the individual points in the cloud. And This was an interview with Joanne Bruna at NYU and Michael Braustein, and they are developing they're researching algorithms that take more like a graph approach.
Okay.
And so the individual points would be seen as a graph as opposed to points in a Euclidean space.
Okay.
Have you looked at that kind of approach to doing segmentation?
I have not personally, but I think it's a promising approach as well. We do use some amount of graphical representation in our method, not at the level of the CNN, but more at the final module, which is the conditional random field.
Okay.
So after we get back to our initial representation. But I do think that approach also is likely promising. Yeah.
Interesting. I guess that's the great thing about NIPS is that you get exposure to all of these different folks working on kind of related things and can, try to pull together different ideas.
Yeah, there's definitely a lot of work that is being done in this field. People are looking into different ways of processing the data. So one of the papers that we compared to was PointNet, which essentially proposed to process the points directly rather than doing voxelization. So there are definitely alternatives to skipping voxelization. The framework that we have in a way, it could, or the conditional random field could still apply to some of those methods, but definitely the point representation is flexible and there are several ways that people could do it. There, for instance, also are more efficient ways to do convolution. There's sparse convolutions that could be done, so that could help with efficiency. The ArcNet is one of the papers that explore that direction essentially. ArcNet. Yes.
Okay.
So essentially trying to perform the convolution operations on the spaces that are occupied rather than the entire volume. So there are definitely various approaches to solve this problem. So
interesting. Yeah. With the conditional random field and the energy function, actually that's not an area that I'm well versed in. Maybe you can talk a little bit more about that. But I'm specifically wondering, is the thing that you did that was interesting was applying conditional random fields and energy functions, or coming up with a specific energy function that worked well in this case?
So the energy function itself was standard, except for the fact that it was applied on 3D points rather than traditionally on images. Okay. So we one of the novel things was that we applied it on the point level. Okay. So the end part of our framework essentially is different in that we're not operating in voxel space. So traditionally, when you're using the CNN and adding a CRF to it, usually the input does not change from start to end the input space. But we sort of have this interpolation layer that helps us to go from a discrete space to a continuous space. And we do further processing within our continuous space with the CRF as well as the trilinear interpolation layer. In terms of the energy potential that we use XYZ coordinates and RGB color as the features. So the energy function itself has two different terms, the unary potentials as well as the pairwise potentials. So for the unary potentials, those come directly from the CNN through the trilinear interpolation layer. And that sort of represents the initial belief of the system about the classes of each point. And then you have the pairwise potentials that are also added to the energy function. And those are the potentials that ensure the consistency between the neighborhood of each point. So.
And is that the piece that you mentioned was kind of more graph-like?
Yes, exactly.
In representation?
Yes, exactly. So we use a fully connected conditional random field. Okay. So it represents relationships between each point and its neighborhood. In this case, because it's fully connected, it actually has a connection between each point and every other point in the point cloud. Okay. So that's the graph representation that we're using.
Okay.
Yeah.
So what's next for this research?
So this research is actually a small subset of a bigger set of problems that I am exploring. So I am interested in, as I said earlier, I'm interested in trying to see how we can enable intelligent systems to assist human beings in their environments.
Okay.
So the first subset of that is scene understanding.
Okay.
You can
What's in the environment?
Exactly. So you can imagine if you give a robot an order to go to the bedroom and get a book, or get the Harry Potter book from my bookshelf. What does the robot need to do in order to accomplish that task? There's various fields that come into that. There's natural language processing, there's vision, there's robotics, and so the natural language processing to first understand the command,
Right.
The visual part, the perception part to navigate through the room, get to the room, identify the object, and finally the robotics part to actually do the interaction and pick up the objects. So I started working on the scene understanding within, in terms of a more detailed scene understanding, identifying objects. But there's also a higher level scene understanding that is involved in those kinds of assistance, which is how do you identify the different places within a building? So how do you know where the bedroom is? And so when we take those 3D point clouds, that information also is not available. So I am interested in looking at getting that higher level understanding of scenes as well, and specifically using neural networks to obtain a navigation focused floor map of environments. So there has been work done in getting floor maps of environment, mainly segmenting rooms between each other, so figuring out the separation between rooms. But in order for those to be helpful for navigation, we need more information. We need the identity of rooms. So we need to know that this is a living room, a bedroom, a bathroom, and so on and so forth. And in addition, potentially we need to know the location of entrances to each room. So once you have that kind of information, you can now plan navigation to go to a specific room. So those are the two parts of scene understanding that I'm interested in. So getting a high level understanding of scenes, as well as the more detailed object level understanding of the scenes.
So for the higher level piece,
Yes.
there's been, as you mentioned, there's been a ton of work that's happened.
Yes.
A lot of it in the robotics community in terms of mapping environments and things like that. Is part of what you're trying to do to be able to identify identify a room, for example, based on what's in the room, as opposed to being given a specific label or something like that?
Yeah, the idea is to identify the room based on what is in the room, so based on the visual information, but also at the 3D level, because there is work that can identify a room based on an image of the room. But if you are in one location of a building and you want to get to the other location, that kind of information is not going to be very helpful. You need to have a map of the environment and know what room, where each room is located. And so we're doing that more at the 3D level and at a higher perspective rather than using images. Yeah.
And in practice, do you envision that a system like this would be used like dynamically or statically? And what I mean is, are we going to have like a mini LiDAR on the robot, and as it navigates the environment, it's making determinations about what the room is? Or more like in the future, all buildings will have, they'll come with 3D point clouds or something on whatever the future version of a floppy disk is.
Okay. I think there would be an initial map of 3D environments, and as the robot navigates around the environment, then it can update what the map looks like, but at a more local level. So if you have an initial state of a room and you pass at a certain point and you see that something has changed, then you can update that in the internal map that you have. So it doesn't need to be updated in real time. Well, the entire map does not need to be updated always, but there needs to be an initial starting point that can be updated locally as the as more information is gathered over time. Yeah.
So the robot would know the kind of overall 3D structure of the environment, but might be able to infer that, well, you removed a bed and put a desk, so this is an office now as opposed to a bedroom.
Exactly. So I guess for an office to change to a bedroom, there will probably be a lot more than like one single change. But even imagining that the room state is still the same, but just a chair was moved to a different location. That can affect navigation planning, for instance, and that's something that is worth updating as well.
And then, it coming from a group that's largely focused on vision, or is your line of research like, in a sense, swimming against the tide? Like, I get the sense that vision folks think that everything will be solved through cameras, as opposed to point clouds and things like that.
Well, I would say, in a way, if you think about Kinect cameras, they, in a sense, are also, they're cameras. They give you 2D data and you can transform it into a 3D point cloud. I think they're sort of complementary. I think 3D can come from images. So in a way, you could say that you're using images if you're, I guess, working mainly with RGBD data. In terms of LiDAR, I guess there is a use for longer range sensors, such as LiDARs. So they can allow you to detect objects that are further apart. And you can try to use reconstruction algorithms, but they're not always as effective as longer range sensors are in terms of data collection. So I think both will have a role to play in terms of solving these problems, and maybe in different applications, images would be better than long-range sensors.
Okay, great. Well, Lynn, thank you so much. This has been a really interesting conversation. Any final words or places that you'd like to point folks to? Or
I guess if you want to follow my work, go and check out the website. The project that I worked on is called SEGCloud, 3D Semantic Segmentation.
Great. And we'll include a link to that in the show notes.
All right. Thank you.
All right. Thank you, Lynn. All right, everyone, that's our show for today. For more information on Lynn or any of the topics covered in this episode, you'll find the show notes at twimlai.com/talk/123. As you know, we love to hear your questions and feedback on the show, so don't hesitate to comment there. Thanks so much for listening, and catch you next time.